May 17, 1952, Roanoke, Virginia. The yard report from visiting diesel locomotive representatives would never fully capture what they witnessed that afternoon. A single Norfolk and Western Class Y6b compound, articulated steam locomotive pulling a freight consist that defied everything modern railroad engineering said was necessary for efficient heavy hauling. Through the coal smoke and grinding steel of the Schaffers Crossing grade, 147 loaded hopper cars moved uphill behind one experimental steam locomotive with timing that seemed impossible to diesel advocates. No multiple unit lash-ups required, no helper engines pushing from behind, no division of the train into manageable sections. Yet this single machine delivered a tractive effort that the entire diesel consists could not match. In competing railroads' operations, heavy freight trains required multiple diesel locomotives working in coordinated sets. Each diesel unit produced perhaps 50,000 to 60,000 pounds of tractive effort at starting. Moving 15,000 tons up mountain grades demanded 3, 4, sometimes 5 units coupled together. Most required extensive training programs and maintenance facilities designed around diesel technology. The Norfolk and Western was operating with railroad philosophy. Competing lines had been abandoned as obsolete. Compound articulation, coal firing, over 170,000 pounds of tractive effort, single-engine operations that transformed what should have required multiple locomotives into one locomotive achievements. 800 miles from diesel-dominated railroads, the most decisive freight-hauling demonstration in American railroad history was revealing itself, not in modern technology, but in the perfection of steam power that everyone said was finished. Norfolk and Western's continued investment in steam locomotives puzzled industry analysts throughout the late 1940s. While Pennsylvania Railroad, New York Central, and virtually every major carrier rushed to dieselize their fleets, N&W's Roanoke shops kept designing, building, and refining steam power with engineering intensity that suggested they knew something competitors had missed. The mathematics seemed to favor diesel. Modern EMD and ALCO units required less maintenance, offered better fuel efficiency in theory, and eliminated the infrastructure burden of water towers, coaling facilities, and ash disposal systems. Yet N&W's accountants consistently showed that their integrated coal-to-rail system produced lower operating costs per ton-mile than diesel operations on competing roads. The Class Y6b represented the culmination of this contrarian philosophy. An experimental compound articulated locomotive that combined proven design elements with innovations specifically targeting the heaviest freight service in American railroading. Crews who first saw the machine in Roanoke's erecting shops during winter 1952 wondered if N&W's engineers had finally pushed steam technology beyond practical limits. John Pilcher stepped from the observation car at Roanoke Station on November 12, 1948, carrying specifications for compound articulated locomotives and convictions that clashed with everything the railroad industry considered inevitable progress. As Norfolk and Western's chief mechanical engineer, Pilcher faced mounting pressure to follow competitor railroads into diesel modernization. The industry consensus was overwhelming. Steam locomotives represented outdated technology from the 19th century, destined for museums and railway preservation societies. Baldwin Locomotive Works, once America's largest steam builder, had delivered its final steam order and pivoted desperately toward diesel production. Lima Locomotive Works faced bankruptcy as orders evaporated. Yet Pilcher and his engineering team at Roanoke shops recognized advantages in steam power that diesel advocates consistently overlooked. N&W's route structure presented unique operational conditions where steam's characteristics matched requirements better than diesel alternatives. The Pocahontas coal region demanded locomotives capable of hauling maximum tonnage up sustained grades where low-speed tractive effort mattered more than horsepower or fuel efficiency. Traditional simple articulated locomotives like the Class Y5 had served admirably, but Pilcher's calculations showed that compound articulation could extract significantly more pulling power from the same fuel consumption. The concept dated to the early 1900s, using high-pressure cylinders to extract initial energy from steam, then routing exhaust to larger low-pressure cylinders for additional work before releasing to the atmosphere. Mallet compound locomotives had dominated heavy freight service decades earlier, but most railroads had abandoned the design complexity in favor of simpler articulated types. Maintaining separate high and low pressure systems required precision machining and careful adjustment that many railroad shops found prohibitively expensive. Industry experts argued that the modest efficiency gains could not justify the maintenance burden. N&W's engineering team calculated differently. Their integrated operations controlled everything from coal mining to locomotive maintenance within a unified system. Complex machinery did not intimidate shops that routinely rebuilt entire locomotives to tolerances measured in thousandths of an inch. The efficiency advantages of compound expansion, when applied to locomotives generating massive tractive effort, could produce operational savings that dwarfed maintenance costs. The Y6b design emerged from months of calculations, drawing board iterations, and heated debates among Roanoke's engineering staff. The specifications called for a locomotive larger and more powerful than anything currently operating in compound configuration. 4 cylinders total, 2 high-pressure cylinders measuring 25 inches in diameter, 2 low-pressure cylinders at 39 inches, all driving 58-inch. Drivers through rigid wheelbases connected by articulated joints that allowed the massive machine to negotiate curves that would derail rigid frame locomotives. The compound articulation concept that Pilcher's team pursued presented engineering challenges that explained why most railroads had abandoned the technology decades earlier. Converting thermal energy into mechanical work through two-stage expansion required precise coordination between high and low-pressure systems that simple articulated locomotives avoided entirely. High-pressure steam from the boiler, superheated to over 600 degrees Fahrenheit at 300 pounds per square inch, entered the front cylinders through carefully designed valve systems. The initial expansion performed useful work driving the front engine, but instead of exhausting to atmosphere like simple locomotives, this partially expanded steam routed through large diameter pipes to the rear low-pressure cylinders. The thermodynamic efficiency was elegant in theory. Steam that had already performed work in the high-pressure cylinders still contained substantial energy despite its reduced pressure. Routing it to larger cylinders where lower pressure could act on greater piston area extracted additional mechanical work from the same initial fuel consumption. The compound principle promised tractive effort gains of 15 to 20% compared to simple articulation. Practical implementation demanded precision that tested Roanoke shops' manufacturing capabilities. The interconnecting steam pipes between front and rear engines had to accommodate the articulated joints movement while maintaining pressure integrity under continuous thermal cycling. Valve timing between high and low pressure systems required perfect synchronization to prevent back pressure that would reduce rather than enhance efficiency. Materials engineering presented additional complications. The low pressure cylinders operated at temperatures and pressures that required special cast iron alloys capable of withstanding thermal shock without cracking. The cylinder walls had to maintain dimensional stability despite temperature swings of hundreds of degrees during operation. Any distortion would cause steam leakage that would destroy the efficiency advantages compound articulation promised. Robert Hensley, Roanoke's master pattern maker, spent months developing molds for the massive low-pressure cylinders. Each casting weighed over 8,000 pounds and required core designs that would create the complex internal passages for steam admission, exhaust, and valve operation. The tolerances for valve seat machining measured in 10,000ths of an inch, precision that pushed the shop's equipment to operational limits. The boiler design represented another engineering challenge that distinguished the Y6b from conventional locomotives. Generating steam for compound operation required maintaining consistent pressure and temperature despite the massive consumption rates of 4 large cylinders. The boiler featured 230 square feet of grate area, allowing firemen to maintain combustion rates exceeding 8,000 pounds of coal per hour during maximum effort. Ash handling became a critical concern with such enormous fuel consumption. The Y6b's design incorporated hopper ash pans with air-operated dumping mechanisms that allowed crews to dispose of accumulated ash without stopping. During heavy freight service, a single locomotive could generate over 2 tons of ash during a typical division run, enough to require multiple disposal operations if handled manually. The first Y6b, numbered 2120, rolled from Roanoke Shop's erecting bay on March 4, 1952, its compound cylinders gleaming with fresh black paint and its massive boiler representing over 600,000 pounds of sophisticated machinery. The initial test program would determine whether Pilcher's engineering gamble would vindicate N&W's continued investment in steam or confirm industry skeptics who insisted diesel represented inevitable progress. Chief Test Engineer Robert Bruce supervised the dynamometer car trials with procedures that would measure every aspect of the Y6b's performance under controlled conditions. The dynamometer, a specially equipped car coupled directly behind the locomotive, contained instruments that continuously recorded drawbar pull, speed, steam pressure, and fuel consumption throughout each test run. The Christiansburg grade provided the ultimate proving ground for freight locomotive performance. 12 miles of sustained 1.2% climb that separated efficient machines from pretenders. Traditional simple articulated locomotives struggled on this grade, often requiring helper engines to maintain schedule with trains exceeding 10,000 tons. Bruce intended to determine the Y6b's maximum tonnage capacity without assistance. The first dynamometer test on March 11, 1952 exceeded every prediction that N&W's engineering team had calculated. The Y6b moved a 12,500-ton train up the Christiansburg grade at 12 miles per hour, maintaining constant speed despite the punishing grade that would have stalled locomotives with inadequate tractive effort. The compound cylinders delivered their promised efficiency, extracting maximum work from each pound of steam generated. Drawbar pull measurements recorded by the dynamometer car told the technical story with precision that silenced doubters. At 10 miles per hour on grade, the Y6b sustained 140,000 pounds of continuous drawbar pull. Peak measurements during starting efforts exceeded 166,000 pounds, a tractive effort that approached the adhesion limits of steel wheels on steel rails. No diesel locomotive combination then operating could match these numbers. Fuel consumption figures provided the economic justification for N&W's steam strategy. The Y6b consumed 17,500 pounds of coal, hauling 12,500 tons over the test division, translating to 1.4 pounds of coal per 1,000 gross ton miles. Competing diesel operations on other railroads showed fuel consumption equivalent to 2.1 pounds of coal per 1,000 gross ton miles when converted to thermal equivalents. The compound efficiency advantage was real and measurable. Yet the complexity that had concerned shop supervisors revealed itself during post-test inspections. The interconnecting steam pipes between high and low-pressure cylinders showed minor leakage at flanged joints subjected to continuous thermal cycling. The valve motion for the low-pressure cylinders required adjustment after the sustained heavy service. These were not fatal flaws, but fatal. They confirmed that compound articulation demanded maintenance attention that simple locomotives did not require. By autumn 1952, Norfolk and Western had constructed 6 Y6b locomotives, deploying them on the heaviest coal drags between Roanoke and Portsmouth. The initial service results appeared to vindicate Pilcher's engineering decisions as the compounds routinely handled tonnage that required multiple diesels on competing roads. Then came the mechanical failures that nearly destroyed the entire program. Number 2122 experienced catastrophic low-pressure cylinder failure on November 8th while hauling a 14,000-ton coal train near Christiansburg. The engineer reported hearing unusual knocking sounds from the rear engine seconds before the right low-pressure cylinder casting fractured, releasing high-pressure steam that enveloped the locomotive in dangerous clouds. The crew escaped injury, but the locomotive required complete cylinder replacement and months of repair work. Investigation revealed thermal stress cracks that had propagated through the cylinder wall from internal steam passages. The massive temperature differentials between steam admission and exhaust phases had caused metal fatigue that the original casting design could not withstand over extended service cycles. The failure pattern suggested that all 6 Y6b locomotives faced similar risks. Norfolk and Western's board of directors convened emergency meetings as repair costs mounted and operational reliability concerns spread throughout the mechanical department. Diesel locomotive salesmen, sensing vulnerability in N&W's steam strategy, pressed their case with data showing that EMD and ALCO units offered guaranteed reliability without the experimental risks of compound articulation introduced. The financial implications extended beyond repair costs. Each Y6b out of service for cylinder replacement represented tens of thousands of dollars in lost hauling capacity and schedule disruptions that affected the entire coal transportation system N&W depended upon for revenue. The experimental locomotive program that was supposed to demonstrate steam's continued viability instead threatened to prove that diesel advocates had been correct about steam technology reaching its practical limits. Pilcher faced the most challenging decision of his career during December 1952 strategy sessions: abandon the Y6b program, accept the sunk costs, and pivot toward diesel acquisition like every other major railroad, or invest additional engineering resources into solving the cylinder failure problem with redesigned components that might or might not eliminate the thermal stress issues. Industry publications seized on N&W's troubles as confirmation that steam locomotive development had reached technological dead ends. Railway Age editorialized that compound articulation represented admirable engineering in theory, but impractical complexity in the harsh realities of daily freight service. Diesel manufacturers increased their marketing pressure, offering demonstrator units and attractive financing terms. Robert Hensley returned to his pattern shop with a mission that would determine whether steam power had any future in American railroading. The cylinder failures resulted from inadequate metal mass at critical stress points where temperature differentials caused expansion and contraction cycling. Redesigning the castings with reinforced sections and improved cooling passages required metallurgical knowledge that pushed beyond conventional locomotive construction. The solution emerged from unexpected consultation with General Electric's Turbine Engineering Division, which had developed high-temperature alloy steels for industrial steam turbines operating under conditions similar to locomotive low-pressure cylinders. Hensley incorporated these materials into redesigned castings with ribbing patterns that distributed thermal stress more evenly across the cylinder walls. When No. 2122 returned to service in April 1953 with its redesigned low-pressure cylinders, Norfolk and Western's most ambitious performance test would either confirm the compound articulation concept or end steam locomotive development forever. The test specification called for a single Y6b to haul the longest freight train ever attempted on N&W's system without helper engines, demonstrating capabilities that would justify the engineering investment and operational complexity. The train assembled at Williamson Yard on May 17, 1953, stretched over 2 miles. 147 loaded hopper cars containing 15,700 tons of Pocahontas coal, plus the locomotive and caboose, created a consist that should have required multiple diesel units or steam helpers to move over N&W's mountain grades. Industry observers from competing railroads watched with skepticism as No. 2122 coupled to this extraordinary load. Engineer Frank Peterson, with 26 years' experience on N&W's heaviest freight assignments, later described the start as the smoothest pull I ever felt from a standing start with that much tonnage. The compound cylinders working in perfect synchronization delivered tractive effort that set the massive train in motion without wheel slip despite wet rail conditions. The train accelerated gradually to 8 miles per hour on level track before approaching the first sustained grade. The Schaffers Crossing grade, where this chapter opened, provided the definitive test: 12 miles of 114% climb that had always required helper engines for trains exceeding 12,000 tons. Peterson throttled the Y6b to maximum cutoff as the train entered the grade, and the locomotive settled into steady work that would either prove or disprove N&W's steam strategy. Dynamometer measurements recorded throughout the climb documented performance that exceeded theoretical calculations. The Y6b maintained 9 miles per hour with drawbar pull averaging 147,000 pounds continuously for 42 minutes. Peak measurements during the steepest sections reached 169,000 pounds. Maximum tractive effort limited only by wheel-to-rail adhesion rather than cylinder capacity. Fuel consumption demonstrated the compound efficiency advantage that justified the design complexity. The locomotive consumed 3,400 pounds of coal, moving 15,700 tons over the 68-mile test division, translating to 1,038 pounds of coal per 1,000 gross ton miles. Comparable diesel operations required fuel equivalent to 2.0 pounds of coal per 1,000 gross ton miles, a 31% efficiency advantage that transformed operating economics. The success generated immediate interest from railroad industry analysts who had dismissed N&W's steam investment as nostalgia rather than sound engineering. Railway Mechanical Engineer published detailed technical analysis showing that the Y6b's tractive effort per pound of locomotive weight exceeded any diesel combination then available. The compound articulation that critics had condemned as obsolete complexity proved to be the key to extracting maximum work from given fuel inputs. Norfolk and Western ordered 20 additional Y6b locomotives based on the May test results, expanding the class to a total production of 50 units by 1955. The design modifications implemented after the cylinder failure crisis proved completely successful, with reliability metrics matching or exceeding simple, articulated locomotives operating on the same divisions. By 1958, Norfolk and Western operated the most powerful steam locomotive fleet in American railroading. 50 Class Y6b compounds handled the heaviest coal drags with efficiency that diesel manufacturers could not match on paper or in practical service. Yet Pilcher and his engineering team understood that their victory represented not the beginning of steam's renaissance, but rather its magnificent final chapter. The economic equations that had always favored steam on N&W's coal hauling operations were shifting as diesel technology matured and infrastructure costs accumulated. Water treatment facilities, ash disposal systems, and the massive Roanoke Shops complex required capital investment that became harder to justify as steam locomotive suppliers disappeared from the marketplace. Baldwin and Lima had closed their erecting shops. Steam locomotive parts that N&W had sourced from multiple suppliers now required custom fabrication in their own facilities. Turbine generators and other specialized diesel components benefited from ongoing development investment that spread across entire transportation industries, while steam technology development had essentially ceased except in Roanoke's engineering offices. The final Y6b performance demonstration occurred on October 14, 1958, when number 2056 hauled 149 loaded hoppers totaling 16,200 tons from Williamson to Portsmouth without helper engines. The feat represented the absolute peak of American steam locomotive capability, an achievement that proved compound articulation had reached the theoretical limits of tractive effort possible with adhesive weight and cylinder design. Industry observers who witnessed this final demonstration recognized its significance. Railway Age's coverage acknowledged that the Norfolk and Western Y6b represents the culmination of 150 years of steam locomotive development, a machine so efficient and powerful that its retirement represents not obsolescence but rather the end of an entire technological paradigm. Norfolk and Western began diesel acquisition in 1959, not because steam had failed, but because the industrial ecosystem supporting steam technology no longer existed. By 1960, the Y6b fleet began its gradual retirement as new EMD SD40 diesel locomotives arrived. The compounds had proven their technical superiority in heavy freight service, but commercial realities beyond N&W's control had rendered the entire infrastructure supporting steam operations unsustainable. The last Y6b in regular service, number 2156, pulled its final revenue freight on December 17, 1959. The locomotive that had hauled the longest train in N&W history was towed to Roanoke Shops for storage, its compound cylinders still capable of generating record-breaking tractive effort that no longer had commercial purpose in a railroad industry that had moved irreversibly towards standardized diesel operations. Several Y6b locomotives were preserved in museums, tangible monuments to the engineering. Brilliance that had proven steam power still possessed untapped potential even as the industry abandoned it. Number 2156 stands today at the Virginia Museum of Transportation in Roanoke, its massive low-pressure cylinders and articulated frame representing the final argument that steam locomotive development had reached, not its limitations, but rather perfection that arrived too late to matter in the commercial marketplace. The Y6b demonstrated conclusively that an experimental freight engine could outperform modern diesel technology in specific applications. The locomotive's ability to pull 150-car trains alone proved that raw mechanical power, properly engineered and efficiently applied, could accomplish feats that supposedly advanced technology struggled to match. The Norfolk and Western Class Y6b remains the definitive example of what happens when engineers refuse to accept conventional wisdom about technological obsolescence and instead push existing technology to its absolute theoretical limits.